everyone, welcome back. Let's see, last time we left off, I think with a statement of Zorn's lemma. So let me just remind you. So Zorn's lemma says if we have a poset in which every chain has an upper bound, then the poset has a maximal element. So if P is a poset where every chain has a maximal element. No, sorry, I just said that wrong. Has an upper bound. And upper bound. Then P has a maximal element. And we said last time that Zorn's lemma is equivalent to the axiom of choice. And I want to say a few words about that. So the axiom of choice, right, just says, I mean, in layman's terms, what it says is if you have any collection of non-empty sets, there exists a set that contains one element from each of those sets in your family. And, you know, I mean, if this is your collection of sets right here, A1, A2, A3, maybe this goes on forever, then, I mean, I think most people's feeling about the axiom of choice is it's obvious. If you have a collection of sets like this, then yes, pick one, pick one, pick one, pick one, pick one, right? What gets weird, or the reason that we need the axiom of choice, is that there are very, how to say this, there's very slithery types of indexing sets, right? So if your family of sets looks like this, A sub alpha, where alpha lives in script A. If this set right here is an uncountable set that is described in a very weird way, then the actual process of coming up with the, to come up with a specific choice function may be impossible. The axiom of choice asserts that such a choice function exists, but it doesn't tell you how the formula is or what this choice function looks like. So you can't expect to sort of explicitly construct a choice function if this set, script A right here, is an uncountable, if it's a strange, difficult to understand set. And so people are somewhat uncomfortable with that. And here's one of the reasons the axiom of choice actually gives rise to some I don't know, strange behavior in mathematics. For example, there's what's called the Banach-Tarski paradox. And what that says, the Banach-Tarski paradox, says something like this. If you have a sphere, it is possible to take the sphere, chop it up into a bunch of pieces, and reassemble it into two spheres that have exactly the same size as the original one. So that's kind of weird, right? And it requires the axiom of choice to prove this. And so that's one of the reasons that it makes people feel uncomfortable with the axiom of choice. And so there are, in fact, people who steer away from using the axiom of choice at all. They do mathematics that is somehow in a safe corner where you don't require the axiom of choice. However, if you don't require the axiom of choice, well, a lot of the things that we're comfortable with, that we're familiar with, go out the window. For example, right, having every vector space, or the statement that every vector space has a basis, requires the axiom of choice. And in fact, I wore this shirt. It's a little cold today, so let me close my window so I can. But the math department, or not the math department, the math club cooked up these shirts a few years ago. Right, this was the shirt that they were selling. So hopefully you can see this, right? Pro axiom of choice. Oh, let's see. I'm gonna back up here. Pro axiom of choice. And then on the back, can you read this? Let's see. Because every vector space deserves a basis. I think that's what it says when I can't read my own back. Oh, sorry. So, anyways, all right. So okay. Sorry, lost choice or lost choice. Lost track of what I was saying there. So, I'm not one of those people that is scared of the axiom of choice, right? I'm okay with having that as an axiom, even though it does give rise to certain bizarre behaviors mathematically, right? It really, to me, makes sense that that a choice function always exists, even though we can't prove it from our other axioms. Okay. So here's Zorn's lemma. Remember, that's equivalent to the axiom of choice. And so we're going to work in the realm where the axiom of choice holds, which means that Zorn's lemma holds. And Zorn's lemma is used then to prove other familiar things. And we're about to prove a familiar statement from linear algebra. Now, proofs using Zorn's lemma, they kind of all go the same. There's a very familiar flavor to them. So let's say proofs using Zorn's lemma have a sort of standard format. Is that how I say it? Standard flavor? I don't know, standard format. Once you've done or seen a few proofs that require Zorn's lemma or that rely on Zorn's lemma, you'll see, oh, they all kind of go the same way. And in fact, you'll see in some books, right, there's a statement of some theorem, and in the proofs, right, so there'll be some theorem, and whatever it is, and then it requires Zorn's lemma, and the proof, you'll actually see this sometimes, it'll say Zornify. And what that means is, all right, you've already seen enough proofs of using Zorn's lemma that you'll be able to figure out how to use Zorn's lemma in the proof of this theorem also. And so it's okay. I mean, there's nothing wrong with using or actually writing out the proof, but Zornify is sort of a sort of mathematical colloquialism, right, for saying, you know how to do this proof, just apply Zorn's lemma. I was at a conference one time, and there were two fairly famous mathematicians. And the first mathematician there, he did a proof. I don't remember what the theorem was, but he had some theorem, and he actually went through the proof. The proof required Zorn's lemma. And he went through all the steps showing, okay, and it's the kind of thing that mathematicians are, okay, yes, we know what you're going to do next, we know what you're going to do next. But anyways, he did the proof, and he worked through Zorn's lemma. And then the next day, another mathematician is giving his talk, and he gets up there. His theorem also requires Zorn's lemma. And he says, so the first, this is not a joke, this is true. The first mathematician says, his name was Jim Cannon. And the second one, who was that? Saradsky, I think it was. It doesn't matter. Anyways, so the second guy says, all right, I have a theorem here. I'm not going to prove it because I was raised differently than Jim Cannon was. I was taught to not zornicate in public. Sorry. And so anyways, what I'm about to do is zornicate in public. I'm going to do a proof that involves Zorn's lemma, or requires Zorn's lemma. So, okay, enough of the talk. Let's get to the math. So here's the theorem that we want to prove. So let's let V be a vector space over a field F. So if capital S is a spanning set, and what do I need? An A is linearly dependent, and so an A, some subset of S, is linearly independent. Then there exists a basis. We're going to call it script B. So then there exists a basis script B for capital V, where A is contained in script B, contained in S. So every time, if you have a linearly independent set and a spanning set, you can find a basis that actually sits inside. So this can then be paraphrased, this theorem right here, can be paraphrased to say that every vector space has a basis. How do you do that? Well, the empty set is linearly independent and V is a spanning set, right? So that tells us then that there's always a basis. And then this makes it even more specific, right? We're going to prove a little bit more than just existence of a basis. We're going to show existence of a basis that lives in between these two sets. All right. So, in an upper level mathematics book, you would just say proof and it would just say Zornify. Now we're going to go through the details just because I think it's good for you at some point in your mathematical life to see a proof involving Zorn's lemma. Okay, so I need to set up a little bit of notation. So we're going to use Zorn's lemma, which means that we need a partially ordered set. So let's let P be the set of all sets X. So it's going to look like this. So I want to focus on, we know that we have a linearly independent set A, we have a spanning set S, and what I want to do is look at the set of all sets X that live intermediate to A and S that are linearly independent. So such that X is linearly independent. This is a very Zorn's lemma type of setup, right? We want to consider all possible objects. We're going to partially order this set of all possible objects, right? So we're looking, our basis, our B is going to be one of those X's essentially, right? So I need to partially order this, so let's say comma right here, partially ordered by inclusion. Now, okay, so what do we need to do? We want to show, so here's our PO set, and Zorn's lemma says if you have a situation where every chain in your PO set has an upper bound, right, then the PO set itself is going to have a maximal element, and we'll show that that maximal element turns out to be the basis. Okay, so let's take a chain. So let's let C in P be a chain. So remember, that's a linearly ordered subset of P. Now, we're going to define, let's say capital U, and what it's going to be, it's going to be the union of all the elements in this chain, right? All the subsets living in that chain. So let U equal, so it'll be the union, I want to say this, D, what do I use, symbol D? Yeah, D. So let's say D element C of D. So we're taking, remember, C is a chain, which means it's a collection of subsets, a linearly ordered collection of subsets, and then we're going to take the union of all those subsets. That's what I'm calling capital U. So the claim is that U is an upper bound for C. And okay. So what would that mean? Okay, so let's see. I kind of wrote this out in steps. Well. Okay, so the first step in this claim is that, so how do I say this? Since A is contained in D which is contained in S, for all little d in capital C. I guess I'm going to have to, I need a little room here. So since we see that U lives in between A and S as well, right? If we have a whole bunch of these things that live in between A and S, when we take the union lives in between A and S. So we see that U is contained, or A contains U, which is contained in S. The second step, if D is one subset in this chain, then D is contained in U. And remember, this is our partial ordering, right? It's the subset. And so what that tells us is that D is less than or equal to U in our sense, right? So we'll say, D, and I'll just use kind of the generic, I mean, I don't really want to use a new symbol. I mean, that's really what it is. But if you like, I mean, it's saying that D is smaller than U in this sense right here. Third thing, so, okay, so let's take some elements of U. So let's let, say, x1 up through x of n be elements of U. And, yeah, so, and suppose that alpha 1 x1 plus dot 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 plus alpha n xn equals 0 for some alpha 1 up through alpha n in our field is capital F. Right? So what are we doing? We're looking at a linear combination of elements that adds up to 0. Right? What am I trying to do? Well, I'd like to show that this is linearly independent, which means that I need to show that all the alphas have to equal 0. Now, each of these x's lives in capital U, which means that each of the x's lives in one of the d's. Now, it could be different d's for each of the xi's, so what do I want to use? I want to use a d sub I. So for each, so this is all step 3 here. For each I between 1 and n, there exists a d sub I in C such that x sub I is an element of d sub I. But C is a chain, which means that each, if you take a d sub I and a d sub j, they're comparable. One is bigger and one is smaller. So since C is a chain, that means that there's going to be one of those d's that's going to be bigger than all the others. So, so there exists, what do I call it here? Oh, yeah, okay. In fact, let's say it like this. So since it's a chain, we can assume, just by reordering things, so we can assume without loss of generality that d sub I is contained in d sub I plus 1. Right? And so that means, so thus, x sub I is an element of d sub n for all 1 less than or equal to I less than or equal to n. All the xi's have to be contained in one of those d's if we assume that we ordered things based on the ordering here. right, then we can just assume that all the xi's are contained in d sub n. It's not necessary to be d sub n. I didn't have to do this without loss of generality thing, but it makes it a little bit cleaner. All right, we've got all the x sub i's inside one of these d's. All of these d's are these. Which means, right, we know that all the x's, I know I had to erase that part, but we know all these x's are linearly independent. Which means that all the d's are linearly independent. In particular, d sub n is linearly independent. So, since d sub n is linearly independent, what does that mean? It means that any linear combination that we have adding up to 0 must require, it only works if all the alphas are equal to 0. So since d sub n is linearly independent, we conclude that each alpha sub I is equal to 0. Okay, so what did we do? We started off choosing these x sub i's in U, created a linear combination, discovered that those alphas have to be equal to 0. That tells us that U is linearly independent. All right, so therefore, U is linearly independent. That's the end of the claim, right? So claim them. Okay, so what did we just do? We chose an arbitrary chain. We showed that that chain has a maximal element. All right, so by Zorn's lemma, maybe I should slow down a little bit. What did we do, right? So let me just back up for a second. So we're working in P. We chose a chain in P. We constructed U. And what do we know then? We know that U is greater than or equal to all of these elements. And it lives inside P because it's linearly independent, and lives intermediate to A and S, right? So U is an element of P that is greater than or equal to, under our ordering, because our ordering is containment, right? So U is greater than or equal to all the elements in C, which means it's an upper bound. So we showed that every chain has an upper bound. By Zorn's lemma, P has a maximal element. And what do I want to call this one? Well, let's call it B. Now, okay, B lives inside P, which means we know that B is linearly independent. All right, so by definition of P, what do we know? We have, well, we have this, A contained in B, contained in S, and B is linearly independent. So B is linearly independent. So what we need to do to complete the proof, we need to show that B is also a spanning set, right? So, say it like this to complete the proof. We show that a span of B, I think I did a script B at the very beginning. I don't know why. Whatever you want to do. span of B is equal to B. There was no reason to use script B in the first place. I was just getting fancy there. Okay, now to show, we want to show that the span of B is equal to V. And to do this, it's enough to show that our known spanning set lives inside span of B. So let me write that down. To do so, it suffices to show that S is contained in the span of B, right? If we can we know that this is a spanning set, and if we can express every element in S as a linear combination of elements from B, that would mean that we can express every element of V as linear combinations of elements from S, which are then it's a mouthful, which are then linear combinations of elements from B. Putting that all together means that every element of V would be a linear combination of elements from B. Okay, so we're going to do this by contradiction. So suppose there's an A. Okay, so suppose there exists a little a in capital S, such that A is not in the span of capital B. Now, okay, remember this from linear algebra. If you have a spanning set and you choose somebody outside, I should say this better. If you have, sorry, I gotta say that better. If you have a linearly independent set and you choose something outside of the span of that linear independent set, then the result is linearly independent. So, so we can say it like this. So then, A union B is linearly independent. And let's see what else we can say. Well, we have A is contained in B, which is contained in A union B, which is contained in S. Is that how I want to write it? Yeah, fine. And what does this tell us then? We know that this is a linearly independent set that lives intermediate to A and S, which means that this A union B lives inside P. And so, A union B is an element of P. But wait now. Also, what do we have here? We have B is strictly contained in here, so B is strictly less than A union B. We have also B is contained, in fact, let's just say properly contained in the script A, a set containing A union B, and this is a contradiction. What we have, it contradicts the maximality of B, right? We have an element that is bigger, an element of P that is bigger than our supposed maximal element. Right, so let's say comma. Contradicting maximality of B. So what does that tell us then? That tells us that no such A could have existed. And so, conclusion, we can say, therefore, B is a basis for capital V. That completes the proof. So now, just a little bit of, I don't know, not clarification, but elaboration. So what this tells us now is that every vector space has a basis, right? So by letting A equal the empty set and S equal to all of V, right? So A, the empty set is linearly independent. V is definitely a spanning set. So we have that every vector space has a basis. Okay, so I'm going to say a little bit more. I want to just so there's the end of that, and so why did I do this? Well, because we're going to prove something about rings, and it will require the use of Zorn's lemma. So I want you to see this in this more familiar vector space setting, and we're going to do a Zorn. We're going to Zornify, but we're going to actually do it. We're going to Zornicate, I guess you might say. Not today, but probably next time. And now, let's talk a little bit about some of the technology, the terminology, and so on that we're going to need. So we're going to be studying rings quite a bit. So the rings, I mean, this is field theory, right? Every field is a ring. So the rings that we're going to consider are always going to be commutative, and they're always going to have one. All right, so so the rings we consider in this course are commutative with unity. And so unless otherwise stated, if I say let R be a ring, that means it's commutative and has one. So so unless otherwise stated, ring, that means a ring equals a commutative ring with one. Remember, back in Math 482, so let's say recall, you may not have had Math 482 with me, but in your algebra class at some point, I think you would have learned about this if you took a class on ring theory. If R is an integral domain, there is the field of, well, sometimes it's called the field of fractions or the field of quotients. I think in 482 I call it the field of quotients. So there's the field of quotients, but I feel like your book probably uses field of fractions. And so let me just remind you how that construction goes. This is going to come up, right? So what you do is you look at, so let's say on R, the ring, cross R star. Remember, R star means everything except for 0. So we define an equivalence relation. So define tilde by ordered pair A comma B tilde ordered pair C comma D if and only if AD equals BC. You can check that this actually is an equivalence relation, and when you look at R cross R star mod tilde, right, it actually is a field under the standard operations, right? So what we do then is we redefine R over S. This is the equivalence class of R comma S. So when we write fraction, when we use our fraction notation, whether you're working in the rational numbers or anywhere else, what this means is, back in the background, it means we're talking about the equivalence class of the ordered pair under this equivalence relation. And then, so under the usual operations of addition of fractions and multiplication of fractions, so under the usual operations, R cross R star mod tilde is a field, right? And that's called the field of quotients or field of fractions. Now, for the most part, we're going to be studying polynomials, right? We're going to be doing Galois theory, which is concerned with polynomials. We will be concerned with polynomial rings of the form, say, well, let me write it. This is the one that we've been studying for the most part in 482. We just studied these polynomial rings right here, right? Polynomials with a single variable, where K is a field. So we're going to be interested in this, but we may need to, in some cases, we might be interested in polynomials that have more than one variable, let's say x1, x2, x3, and so on. Or, so we could say, or K bracket x1 up through, say, x sub n, right? Polynomials with n variables, where capital K is a field. Now, in the case that K is a field, this ring or this ring is an integral domain, which means that the field of quotients or field of fractions exists. So since K bracket, let's do it in the general case. So K bracket x1 up through xn is an integral domain, the field of quotients exists. Okay, so what will objects in the field of quotients look like? Well, it's going to look like the equivalence class of polynomial over polynomial. And so the field of quotients exists, denoted, oh, that should be a lowercase, denoted, K parentheses x1 up through xn. So the elements here, these are equivalence classes of polynomial over polynomial. Or I guess I should say it's polynomial over polynomial, those fractions, which is an equivalence class. So elements of K parentheses x1 up through xn are, well, what are they? They're called rational functions. Or rational expressions, I guess is another way. So, or we'll say rational functions or rational expressions. Yeah. I think this is a good place to stop, and so we'll pick up with this in the next time. I'll let you digest this. We just did probably your first proof involving Zorn's lemma. Hopefully you enjoyed that, and we'll see you next time.